Okay, good morning, everyone. Today we have Avi.
All right, hi.
What an introduction.
Today we have
Yeah.
It needs no introduction.
I'm very impressed by my very young audience over there. So I want to tell you about points and lines.
Really?
Yeah, the abstract says it. Yeah, so luckily points and lines don't need introduction, right? Because they were studied since the Greeks, and somehow we've discovered that one line of type of questions about them is actually related to some computational complexity problems that we are struggling with, and I'll tell you about these connections. I said it's a good time to, what I describe is really old, like papers from about 10 and 15 years ago, but I only gave one talk about it, and I love this work, so I subject you to them. It's a good time to talk about points and lines also now, because there are breakthroughs happening.
I'm tempted to ask what's the point?
Yeah. So the criteria conjecture, as you all know, was solved recently, and this was the basic long-standing problem about points and lines. And also, as you see, I'll talk about some connection to codes, and in particular, locally decodable, locally correctable codes, and breakthroughs here. Peter talks about him. Rick talks about problems with points and lines. I'll tell you what kind of problems I'll talk about, and I'll demonstrate it with this, what's called the Sylvester-Gallai theorem. But it's not really Sylvester-Gallai theorem, it was Sylvester in 1893, and independently Erdős in 43 was to conjecture it. And then it was solved independently by Gallai in 44, I guess. And also earlier and independently by Melchior. So it really should be called this theorem, this way. The question is very, very simple, and I stated it in the abstract. Imagine that you have here a finite set of points in the plane. In the plane, I mean, you can put them in a plane or in Rn. Doesn't really matter for this problem. And suppose I tell you something very strong locally about this point.
Is it the same n?
Yeah, if I have n points, you can always put them in n dimensions. You can put infinity here if you want, but without those generalities n. But for this problem, you can think that the points are on the proof wouldn't mind for the proof it wouldn't matter. And suppose I tell you, so here is a bunch of points. And I tell you, no matter how I pass the lines through two of them, I hit a third, okay? The condition exactly is that, so in general, when I talk about lines, I really mean lines determined by the set of points, okay? So here's the theorem. If given P, so that for every line, every line contains points, always points from P. So how can such a set look like?
I mean, every line between 2 points.
Yeah, every line I'm talking about is determined by the point. Yeah, and with point, I mean point form. So, yeah, okay, one, two, yeah. So it can look like this, like. It cannot be on the line. Any other suggestion? Okay, good. How many people have seen the proof of this theorem? Okay, few. I'll show you this 1 minute. Okay, so this condition implies that life is like this, so the points must be collinear. What's the proof? I'll give you a proof by Kelly. There are several proofs. I all use very strongly the fact that we are in the reals. So I should mention here that this is really depends on the field. So this theorem is false for finite fields. And false for the complex. So it's really, it would matter. I'll mention some things about this. Okay, let's see the proof. The proof says, okay, we have a finite set of points. Assume they are not collinear. If they are not collinear, there are some point which is not on some line. Okay, so let's collect all these pairs, lines and points, P not on L, and look at the distance between the point to the line. Okay, distance is the usual sense. And let's look for the minimal distance. Okay, it's a finite set, it has a minimum, it's non-zero. So there must be some line here and some point here. So this is L, P, and the distance here attains. But we know that this is one of the lines. It has at least 3 points, so at least 2 of them are on one side. Well, this point can be here, it doesn't matter. Okay. Now look at this line. L prime. Look at this point, D prime. Clearly, this distance is shown. Okay, a contradiction. Very simple proof, but you know, Sylvester couldn't do it. He waited 40 years to be resolved.
Does this fail if P is infinite?
If
It's supposed to be infinite.
take the whole plane.
Yeah.
No, it's the point making. This is really the reason that in finite fields it fails. Take all the points for your excuse to the D and take P to equal this set. This is a finite set of points in a over, you know.
Quantitative analog for finite.
Yeah, we'll talk about, yeah. Peter can tell you some, we'll see the connections and then we'll talk about this. But also for the complex numbers, somebody can guess what the counterexample might look like. Some numbers you will see. So with the complex numbers, you can take an elliptic curve. So we are in T squared. Take an elliptic curve. I'm not very good at drawing these things, but well, elliptic curve is infinitely many points, but bear with me. What we know about so this is also the complex plane. This is a 4-dimensional object here. This was for a second, but in elliptic curves, if you pass, you have this property that every line is on contains at least 3 points. Another thing we know is that some, so that's an infinite set, it doesn't help us, but some elliptic curves also have, so these triples are actually a group. There is a group law telling you that you really add these points and get this point. And this is it's a group and abelian group. And this group, for some curves, has subgroups which are finite. So take a finite subgroup of this, and you have one over the complex plain a counterexample to this.
Where does the proof fail?
Then, yeah, where does the proof fail? So the distances.
Lines in a complex field are actually more like planes. Right? If you think of this way, kind of weird.
I guess the whole picture is just.
No, yeah, no, I cannot. It was a proof by picture, which I cannot draw.
Well, the proof of picture was fine for R square. It was even difficult for me to do it in R cube.
Yeah, but over R cube, it's the same picture.
Same argument.
Yeah.
Yeah.
It's exactly
So I think
same.
that's what it
So
doesn't
actually-
almost look like what's the difference between R cube and R4 and C square, right?
Sorry. So Searle conjectured over C and this is a theorem. So this is a theorem by Kelly and Kelly. So this was maybe in 60, and this was a day Switzerland. So we proved this. And we'll come back to this theorem because actually the proof uses algebraic geometry and highly non-trivial. It was proved, so this is using algebraic geometry, and there was an elementary proof by Elkis and this no. I'll mention how this can be proven from the type of results I'll discuss in a more elementary and more uniform way later. Okay, so these kind of questions, of course, once they existed, they were generalized, and I want to tell you about some generalizations. It's not going to be very important for what I'm going to continue. I just want to give you a sense of, other games you can play with this type of questions.
Dimension at most too. It's like you're in C2.
You're in situ,
dimension.
a complex plane, you cannot have points that span higher dimensions than 2 in the complex.
But you're in C2. So you mean like in
No,
R4?
I'm not in situ. So assume this set of points.
Oh, in CD and then
Yeah. Yeah, so
and so.
P it is n, but the dimension will be at most. Yeah. So yeah, these local conditions impose a very strong global condition. The dimension, the real dimension, but the affine span of this point is very low. Okay, if you want all these conditions for. So what kind of other type of results of this nature? One is for other fields. Another is this colored version. So the Motzkin-Rabin theorem is one of this kind, and it says the following. It says, suppose you have two sets of points. So it should not draw them like this, but let's say red and blue. And maybe they are both of size n. Finite. And all you demand is that there is no monochromatic line. So no monochromatic line is tells you about some circles, right? It doesn't tell you if anything if you move a line like this. But if you take a line between this and this, sorry, the opposite. If you take a line between these 2 points, maybe it has no other point. But the line between 2 red guys has to hit the blue one. So you have many scribbles. And we'll be interested in many because rather than all, because we'll have quantitative generalizations of the theorem. Okay, well, not everything happens, but most or some fraction, some small fraction, 1% of these conditions, local conditions are. Okay, so that's one, and we'll see that this is also relevant. Relevant, I mean, also for the applications I mentioned later. So it's really nice that all these questions that were asked abstractly somehow hit, complexity theoretic applications. Another one I want to mention that also is relevant is higher dimensions. So what I talked about there is about every line, which is a one-dimensional object passing through 2 points, contains a third. You can ask about, I suppose I take t points that are, or t plus 1 points that are linearly independent. They span a t flat in space. What happens, suppose every such flat contains another one. So there are results by Hansen started at least in 61, and then for this, Wigderson. Yeah.
What was the result in the previous theorem?
Yeah, very good, thank you. Yeah. Oh, thank you. Yeah. Conclusion. So, the type of theorems, okay. There are several types of definitions for higher dimensional flights. I will not be too precise, but basically, if for every, let's say, P1, P plus 1, which are linearly independent, so that they span a T flat, another Pj in the flat defined by this. So just the same analog of the line thing, you just read it higher. So every T flat contains one extra point beyond what it should. Then I think this holds over the complex numbers also, so it cannot be improved. And we'll see why this also matters for complexity. So this is more or less the type of results that we want approximate versions for. So the connection, the inspirations between these problems complexity started in 2 papers, one by Mir and Spilka. Higgs and Kayal and Salaf. Nine. And the 2 problems I want to tell you about now are 2 basic problems in complexity theory, and the connection between the 2 was here, the connections of these 2 to this discrete geometry was here. So what are these 2 problems? So I'll talk about actually 3 problems, but the third later. So one is the PIT, polynomial identity testing problem. Testing problem. And the other is the LCC problem, also LDC, but not mentioned it. So this is locally error correction code. And I want to talk about matrix rigidity later. It's another basic problem in complexity theory. So some people here know very well all these problems, some I don't think do. I'll tell you shortly about each, and we'll see the connections to the point line incidences. But ask me questions, those who don't, have not seen it and are interested. What's the polynomial identity question? We are going to look at, we have some field F, and we are going to look at some formula, arithmetic formula. So by this I mean just using plus and times, arithmetic formula, over this field. So how does this look like? It can look like plus and at the bottom we have variables like
In an expression,
expression, exactly. You can call it, some people call it formula, some expression, what we are used to. Whenever I put a plus, I allow, arbitrary constants in the field. So when I say plus, I really mean a linear combination. Okay, so that's the formula. Suppose I give you a formula, so it's in some variable. So formula for each f, and suppose f is some number of variables. And I ask you the basic question for given f. I just draw you this formula, right? I give you as an input the formula. Is f identically 0 as a polynomial? And Ming in his talk already mentioned that this, maybe natural problem, but doesn't look very foundational
all the reals,
over any field. Fix a field and ask this question.
field, okay.
Yeah, if the field is F2, it's NPR, or finite field. Fixed finite field is NPR, we know that. But think about large fields like, rational complex and so on, or think about any field whose number of elements is bigger than n or n squared. Okay.
I think in general, it's not, this is a real close, if it's, what kind of field? Real close.
Whatever you
field.
want. Whatever
Real
it is.
close fields, we know it's all
Yeah, we
decidable,
know,
I think it's
but
all
decidability, it's decidable, of course, it's decidable. This, in fact, solvable easily in exponential time. But Ming mentioned two things. One is that this problem is easily solved in probabilistic polynomial time. Why? Pick random values to the variables from some finite set, if the field is big enough. Then, with high probability, if the polynomial is non-zero, it will be, you'll get a non-zero output. And of course, if the formula is zero, then you only get zero. So I'm not writing this down. This is the well-known, the Schwarzschild lemma. Right, and we don't know, so that we have a very simple probabilistic algorithm, and we don't know a deterministic algorithm. So this question is open. Is this problem solvable in deterministic polynomial time? And as I said, this looks like one of many problems you can study, but it's a fundamental problem to complexity theory, because if it is in P, so this is a PIT problem. PIT, polynomial identity testing. So the polynomial is computed by the formula. I want to know whether it's identically zero. And Well, you may mention this fundamental result of Cabanet and Pagliasso. Which tells you that if it isn't, if there is a deterministic polynomial time algorithm to this innocent problem, then you prove something like P different than M. Okay, so all you need to do to prove something very close in some sense to P different than NP is find a polynomial, deterministic polynomial time algorithm for this. Which will actually blow your mind because an algorithm for a problem actually proves that many other problems are difficult. So you can wrap your mind around this. Yes, we get circuits low bound. So this is why it's important to study this problem. So the paper of Dwyer and Schwicker suggested that we approach it, from the easiest problem up. So what's the easiest formula? This is easiest formula, how can a polynomial given simplest form? I give you the monomials. So let's look at what's called depth 2. So this is how a polynomial is normally given. Right? This is sum of monomials. Sum of monomials, but I give you the polynomial and I ask for polynomial time algorithm. If I give you the polynomial, this will be 0 only if all the coefficients will be 0, right? Polynomial is identically 0, so that's easy. So depth 2 is easy. You should think that depth 2 can also have another form, which can be a product of linear form. And here we have some coefficients. But what is this? This is This is a product. So here we have a product. 1, 2, I don't know, M, some linear forms of the variables. So how do you know if the product of linear forms is 0? It can be 0 if at least one of them is identically 0. And again, you can easily check. So really the first non-trivial case arises when we are in depth 3. We have 3 layers in our formula. Okay? So let's see where I want to proceed. So let's look at the sum of products of linear form. Okay, so this is depth 3. And that's already quite challenging. And in general, we don't have a polynomial time algorithm even for this. Okay, so let me tell you what they observed, and here we start seeing the connections. So they suggested simplifying further and restricting this number to be some S, maybe a constant. Okay, if it's 1, then it's really depth 2, so it's 2 of them. So it's really what we are asking is whether A equals B, where A is the product of some linear form, and B is another product. And these guys are linear form. Let me say linear and not affine, it doesn't matter, but let's say linear. Okay, how do we test this in polynomial time? Anybody? I give you 2 products of linear forms, 2 sets of linear forms. Please. Okay, yeah, maybe it's too trivial. Okay, we have unique factorization. If these are identically 0, then then this one set is or multi-set is a permutation of the other. That's easy to check. Okay, so the first really non-trivial case is when S equals 3. And we have some A plus B, C, identically equal 0, and C is also a product. Some linear thing. And that's what they tackled first, Weir picked up. And they made the following observation. Suppose we force, so we just declare or reduce dimension, suppose we force AI to be 0. So we just take some variable and fix it so that the one right as a function of the linear function of the others to make it 0. Suppose we force Bj to be 0. If this equation holds identically, we have a product of linear form 0, which is 0, which means one of them must be 0, right? So this implies that there is a k, that the ck is 0. And now I think you should see the connection. What are linear forms? They are points on a line. So this can happen if there is a linear relationship between.
Sorry, I think I will ask you, how do you force the AIs to do that?
I set some variables to be the linear function. This is a linear function of the variable.
Yeah.
I make one variable equal. I set it to, I substitute for it the linear function that makes AI equal to. Right?
You choose a point that makes a, make that.
No, I substitute the variable. If I know that x1 plus x2 plus x3 is 0, let me call x, I substitute for x3 minus x1 minus x2.
Okay.
And then I get another formula. Okay, so after setting this, something like this must be 0. So these are, and what does it mean? It means that there is a linear relationship between these three vectors, which are 3 points in R to the n. Okay, so this really means the line A and Bj, which are points, contains. And we have many, we can do it in all the possible ways. And what do we get? We get almost Sylvester-Gallai, but actually a colored version. Right? We really have 3 colors, and if we pick 2 points from 2 different colors, we hit that. The line will contain a third. So it's a problem of exactly the same kind. Okay, so that's one observation. And now it's back to the other problem. And so there is an intimate connection here, right, between this fundamental problem and this point of line incidence. Here's another one, and this is the people who came to Peter's talk. We remember it, but I will not assume it. So this is this was PhD. And yeah, maybe I should say this paper, they proved the result. They proved that under this condition, so Weir and Spilka proved that this condition implies rank or dimension of the AI on the BJ case, all these all these points is some polylog. So that's already a strong, so we had started with this local condition, and strong dimensional probability means, what does it mean? It means that you can substitute the variable so that you have only like polylog ones remaining. And then you have a problem with fewer variables, you can just, either expand it, and then it's slightly super
I have a
polynomial.
question. Is it clear you can take any AI and BJ and force them both to be 0 at the same time?
Yeah. If you can, then the whole thing cannot be identically 0.
If you cannot, then it's not cannot be 0.
Yeah. And actually, Kayan and Saraf put the strongest theorem, this dimension. So it was times some function of S, which is not just for 3, they prove something more general, and they prove that this is more something like S to the n. So independent of n, a constant number independent of n. And you see that this immediately, again, you just need to, you have a finite number of variables you can, just explain the formula in these variables and a polynomial time algorithm. It actually gives a stronger result. I described the polynomial identity testing in what's called the white box form. I give you the formula explicitly. Another thing you can imagine is what's called black box form, in which I promise you that the formula is of this structure, but all I let you do is evaluate. You can evaluate it. You can ask a black box for values on some vectors of input. And it turns out that this, both of them, in fact, lead to black box algorithm. But I'll not discuss that. Black box algorithm.
So there is a polynomial time algorithm for the.
For constant testing. For constant testing.
This is like the 3-color version.
This is like a 3-color version, and in fact, it's not, it's S. It's not 3-color, it's S-color.
It's S-color.
S-color. And it's S-color in this setting of higher dimensions, because you set all but one and they apply another one.
Oh, this was.
Yeah, so they actually prove, Karan and Saraf prove a colored version of Bonus-Edelstein, and that used it. And it's delicate. And anyway, I'm not going there, I just want to show you the connection. Okay, so any problem, any questions about this polynomial identity? Okay, so I want to talk about LCD, locally correctable code. Miriam Shipik will talk more about LDC, locally decodable code, but I'll talk about LCC. So what are LCC, locally correctable error correcting code? The idea is that in coding theory in general, you have some message you want to send. Maybe it's some long message over some field. And so you pass it, but there are going to be errors in a communication channel, so you put redundancy into some code, and you get a Y, which is much longer, let's say F to the N. And what you hope for that in this long message Y, which is N bits, Y was sent over the communication channel. Some errors occur adversarially, let's say some small number of errors, maybe delta in errors, if the error rate is delta. Let's put epsilon n because I use delta for something else. Epsilon errors, there should be a way to recover from that. So the code is such that you can, there will be an algorithm that detects the errors and removes them and figures out what the code word is, and therefore figures out what the original message was. And that's a normal situation. I'm going to talk only about linear codes. So really, we have a matrix. So it's a linear code. Is that this encoding and also the decoding are linear. So there's a matrix, which I call it P for some reason. Here is X, here is Y. So just a linear code. Now, this is, I describe normal error correcting codes. What are locally correctable or locally decodable codes? This is a situation where you don't want to know the whole code word. Eliminate the error from the whole code, but all you want to know is what is the value in this position I. You want to know what's the value in this position I. That's all you want to know, but you are also restricted in what you are allowed to look at. Instead of looking at the whole code word, I allow you to look only at few positions, some constant number of positions. Okay, so there should be an algorithm that given I picks some Q queries, let's say J1 and JQ, and you want that, so it looks here, I don't know, J1, J2, and so on. Look what's here, what's here. Of course, we don't know which of them are errors and which of them are not. And then from this squares determines yi, so it reads the squares, it reads y in this position, and determines yi with high probability. Let's say 90%. Okay. And you want this for every I. So for every I. For every I, you want to be able to do this. So that's the locally decodable code. And then you ask the usual questions. What is the rate? How much error can you tolerate? And so on. And in the linear case, you can see that determining yi really means that you want yi to be in the span of the yj, right? You want a linear relation. And you see already, why I call this P, this generator matrix. It's really, so in this case, in the linear case, we want yi to be in the span of yj1, yjq. Now, how can you tolerate these errors? There are epsilon errors. Well, one way to do it is to have many disjoint such subsets of queries, right? So for every I, you want to have S1, S2, SR1, SI maybe. K is of size Q. And we want yi to be in the span of this slide. For every I. Okay. And if K is this K, or let me call it delta, if delta is greater than 100 epsilon, then you know that most of these tuples, Q tuples, will not contain an error. So in probability 99%, you will decode correct. Okay, so that's linear locally error correcting code. So what's the connection? You see the connection, I wrote it down. There are linear spans or points. This is really, what does this mean? This means that the ith row here is really in the linear span of the J1, J2, and so on. So these are linear conditions. Now, we are going to restrict ourselves to the easiest case, of Q equals 2. So this is well understood. I still want to tell you about the case over the reals or over large fields. And doing something like this, still even over the reals for higher Q is still open, because we are going to prove something really strong. Namely that unlike finite fields, in these infinite fields, or even if Q is a bit, so if the field is large enough characteristic, there are no locally correctable codes. In the case of finite fields, we do have them, even though they have loud degrees. Okay, so with this in mind, I want to formulate now the approximate version of the Sylvester-Gallai problem for Q equals 2, and then I'll state the theorem, and then we'll prove. Any questions about it? Say, I didn't motivate locally correctable codes and locally decodable codes. For those who don't know, they are very related to both error correction, but also constructions like PCPs, and other things that come up in interactive proofs and computational complexity. So again, very important. I would not say that over the reals are very important, but they are interesting. Okay, so let me formulate now the approximate version. And if you can, Sylvester-Gallai talks about all triples. You can ask about most triples or most lines and so on. But from the definition, we'll tailor it to what the LCCs require. And here is what I will call a delta P. There is a definition that we will build. P is a delta Sylvester-Gallai configuration. So it's all over the real now. It's a delta Sylvester-Gallai configuration if for every point P in P, that's the I, if you want, so Pi, a line, lines through P contain, I would say the special lines. Special lines, these are lines with at least 3 points. Now we will have lines that don't have 3 points in them, but if you just look at lines that have at least 3 points in them, they contain at least delta and other points. And why is this exactly what we need in 2 LCCs? Because if you have a point P, and that's for every point, we want this line. So here is P, and here are the special lines to it. And maybe here we have 2 more points, and maybe here we have, and here we have, so on. We can pair up the points. Like you take, this will be our S1, this will be our S2, this will be our S3. Well, here we may lose a point. Like this.
And this is the if, what's the then?
Yeah, I know. I'm just, no, that's a definition. It's not yeah, it's a definition. I'm just drawing a picture of
definition. Yeah.
the definition. You want these points on these special lines to be some constant fraction. Of
Yeah, yeah.
Okay, now I ask you the same question I asked you before. Suppose delta is 1/10.
Definition doesn't force to have any special lines or any 3 rich lines, right?
No,
You said that there are many or there are many.
Yeah,
special-
delta, if I'm saying that there are at least delta n points on special lines, so there must
But
be.
what are the
It
special
can be the same line. It can be one line, it can be many lines. I don't count the line. I count the
It can
number.
be no line. This
Points.
allow for no special lines.
So
On all lines, then you can.
No special, suppose there are no special lines.
Then it doesn't satisfy the definition. It's not a delta.
No, it does, because if a special line must contain delta n points, but if there are no special lines, there's no problem.
I give you a generic set.
Okay, I
without-
didn't say it right. No, every point, the special lines who there are no, so it doesn't have any points on it. I want it to have delta n points.
No, but suppose there are no special lines.
Then this will be 0, and 0 is less than delta n.
No, but you say that. What is the definition? It says
It's a set of points satisfy this condition. I call it a
for
delta.
every P there exists special lines or what?
If I look at all special lines,
Special lines are-
that's the special lines for this point.
Suppose that P is generic, there are no 3 rich lines.
There are no special lines.
It says that for every P, all the special lines through P contains more than delta.
Yeah, there are no such points, so
So
they
it
don't
is
contain.
satisfied.
No special lines, she's asking, no special lines.
Okay, let's see what the,
No, no,
Then automatically the definition is.
he's satisfied, but he says it
Yeah.
doesn't.
So generic set of points satisfies.
I can rephrase it, let's say, for every point, there are delta n points on special lines. That makes you happier.
I think so. Okay,
That's what I meant.
okay, let's see the conclusion.
Yeah, I
Let's
can,
see if,
For the conclusions, I want you to think about how to, what's the least dimension you can put such configuration in.
Avi, do you in particular mean that every point participates in at least one special line?
Yeah, of course.
Okay.
At least there's endpoints on special lines. Okay. So how would you can you put it in higher dimension than one? Of course, polynomial points satisfy this. How would you make points that span a higher dimensional space where still these special lines for every point contain at least 1/10 of the point? Any idea?
You can take 10 lines.
I can take
10 lines.
10 lines. I can take 10 lines. And they will not be like this because then they'll be in 2 dimensions. But I can take 10 lines and take these 10 different coordinate directions and put, 1/10 of the line n over 10 here, and then n over 10 here, and n over 10 here. In 10 different directions, and I have points that span 10-dimensional space, and they do this. So we can do 1 over delta. Can we do better, bigger? Okay. So now I'll tell you the theorem, and then I'll prove it. Just they consider the age of the speakers and maybe oil the So I want to tell you about 2 papers, one with Barak, here, with Ayo. Small. 11, and second with the Shubhani Saraf in the rear. 14, so that's how all these results are. And here we prove, I'll give you more details about these parameters, but here we prove that this is delta Sylvester-Gallai configuration, and then the dimension of P most. And here we put this result to the optimal. Basically, you cannot have higher dimension than this set of lines. And one interesting, I'm going to prove this. This is a refinement of the same techniques. I want to prove this because it contains already all the ideas that I wanted to talk about that I mentioned in the upside, that it combines somehow nicely some combinatorial and algebraic and analytic ideas, and it's all very simple. I think you need to do a few more Koshish boxes and other things, but I want to say 2 things about this. Here, one thing that this does, it's not obvious from the statement, but you can wonder what, it's all over the complex. So now I'm over C. All these results.
Not the reals.
Well, also the reals. Okay, so this proof all the results are over C. And here I want to say that this implies over any characteristic 0 or large enough. Yeah.
Meaning bigger than the number of points.
No, much larger. This uses effective Null-Sollenz. So, which I can explain at the end if you want, why, how you get this. It even seems to contradict the fact that over finite fields we have LCCs. But it doesn't. Well, we may get to this at the end if anybody wants to ask. But anyway, it implies a rational reals and large enough characteristic. So first I want to say is that even this result, so it means no two LCCs over such field. Right? Because I tell you, you can encode only a constant number of values. Right? It doesn't matter what n is, there's no bound of n, you cannot. So it's a useless code. So that's one consequence. Here it turns out that if you work hard enough, you can make this constant small enough so that if delta is 1, delta is 1 is the case of Kelly's theorem. So it turns out that it implies Kelly's theorem. And the last thing I want to mention is about this result, is that there's a bound there. Now let me say it now before the break, and then I will not have any applications remaining to talk about. So what's in here turns out that this paper implies also a rigidity bound, a matrix rigidity bound. So I'll tell you in a few minutes what this problem is. It's another very basic problem in computational complexity. And here's the problem. So now we just give all this to matrix rigidity. What we are looking for is a matrix A, and we want it to be explicit. This is interesting for any field. So we are in parentheses now. For any field, if we would like a matrix, let's say n by n, and explicit, I mean that we should have a description of the family of matrices for every n that we can easily generate. And we say it's RS rigid if for every change of a small S entries per row, the rank remains, the rank over F remains at least, is at least n over. Okay, so what do you want? You want a matrix that will be high rank, but will remain high rank in a small border around it. Okay. Of course, the changes are whatever the field allows. If you are over F3, you can change it to any value F3, and then you want the rank over F3 to remain high. The important parameters, one, an amazing paper about graph theoretic arguments leading to computational results. It shows that if you have if A is n over 100. Sorry, I should have also written here R because I defined R as rigid. The rank is at least R. If you have rank n over 100 n to the epsilon rigid, it is matrix. Then AX, simply the linear function, the linear transformation, AX is not computable. Not computable by circuits that have circuits C. Here is X, and this should be AX, so be many outputs. this should be X, where the size is linear and the depth is logarithmic. To our shame, for 70 years of attempts, we still cannot prove that any problem cannot be solved by linear size and logarithmic depth. And this is one way to obtain such a long one. This proof is beautiful and not difficult, but are not true. Okay, good. So break 5 minutes, and I'll prove the.
The delta version of.
Yeah, just a second. I just said something at the end of and some people said, what's the connection? Yeah. What can we say about rigidity? We cannot prove it. We cannot. We don't have a explicit matrix which is rigid in these parameters. But actually, if you relax it somewhat, we know something directly from this theorem or from the more general theorem implying this, and I'll tell you what it is. So one natural choice for, well, how many matrices do we know? So a few nice matrices. So the projective plane matrix, is an n by n matrix. I will not describe it exactly, and it's not important. It has the 0-1 matrix, which has about rows n ones per row, and it has a full rank, and you can imagine or conjecture that it satisfies this condition. Okay. Maybe it is. We don't know. We don't know how to prove anything like this. But what follows from here, from the techniques here, is that changing, not just in, I forgot to say, now about rows n ones per row, but 2 rows have only one common. So 2 lines intersect only in one point. Changing at most n to the epsilon 1. I don't allow you to change zeros. I allow you to change ones any way you want. In every row, leave rank bigger than. So, you know, this follows from this line point business. Doesn't give us what we want. I don't know if there's a way to. What?
How does it follow?
No, I didn't explain how it follows, and you will get a glimpse later. But it's from the techniques proving this, yeah. So you're concerned about the delta G configuration.
Basically, if I didn't think about locally correctable codes, but instead I was thinking about the Sylvester-Gallai theorem or Kelly theorem, and I want to find a robust version of it.
Yeah.
Then I mean, maybe I wouldn't say through every point.
Right.
Basically, I would say, suppose I know the delta n of the points are on special lines.
Yeah, you can, there are several analogous things that you can say that quadratic number of triples lie on special lines.
Right.
Right, and it turns out that all you can get, we have theorems about this also, all you can get is that a constant fraction of points lie in low dimension. Because you can take, then you can throw other things that wouldn't hurt the statistics, right, in high dimension. So you can get the best you can get, also for this. So this average out 2 weeks is like in totally correctable code. You demand that half the forms that decoding, and then it's much easier. Yeah, it's very similar. So that's really the right version if you want the local to global, a strong local to global.
Avi, in this version have any application?
Sorry?
Does this kind of testing have any application? Like this robust version?
No, that I know of, no. Yeah. Well, maybe this would be an application. That would be really, really nice to have rigid matrix over the reals. I don't know how to do it. Okay, so we want to prove the theorem at the top. We have a delta Sylvester-Gallai configuration, and we want to prove a dimensional upper bound. So let's look at this set of points B. So this is, and we want to prove, so we want to prove that the columns here are independent. If it's a code, you want the column to be independent. We want to prove that D is some, some constant of the delta square. So how can we want a dimensional upper bound, and the way we get it is by a dimensional lower bound. What do we know about codes? Well, what do we know about P? We know that if we fix any row here, a row I, we know that special lines for this. I mean, we can have these pairs, right? This pair, this pair, this pair, and so on. Delta n fraction of pairs that span this row, this point, and this is true for every point. So let's write the parity check of this matrix. Okay, so it will be an n by whatever m matrix here, and let's say for the row one here, let's say we know that we have not one, A1, A2, A3, that's for the first pair, and A1 prime, A7 prime A10. Right, so we have these triples which tell us the coefficients of the linear combinations that have to exist here. And we do this, so we have, let's say K, this is the sign of D, right? And then we have, for the second, we have here B1, B3, B1 prime, B2 prime. And so on. So we do this for every one of the rows. So we have at least, I don't know, Kn delta n squared rows here. And what do we know about this matrix, about these two matrices? Let's call this matrix M. See, this usually is a generator matrix, is a parity matrix, but because I call this P, I have to call it something else, excuse me. But we know that this gives us a zero matrix, right? So we know that D is the smallest, or is the smallest minus the rank of M. So we need a low bound on the rank of M. We in fact want to prove that it's very close to N, like within a constant of N. This looks like a harder problem. Sometimes, I mean, it seems like proving a constant upper bound is much harder to prove that this matrix has rank N minus very, very little. But we'll do it this way, okay. So first I want to say something general about this type of problem. So we want a low bound for this, even though we don't know what these coefficients are. So somehow we want a low bound that depends only on the zero non-zero structure of this matrix. There are families of such questions, trying other properties that you want to infer something about the rank or other parameters of the matrix just from zero non-zero structure, or sometimes plus minus one structure. So the problem of sign rank, which I'm sure many of you know, is I give you a plus minus one matrix, and I want what's the minimal. I ask what the minimal rank it can have if you change it arbitrarily to real values which preserve the sign. And that's important in communication complexity, and that's a solution by Forster, which is beautiful. And there are other things in combinatorics, Hamada conjecture, and so on. There are many questions of this type, and also this is another question of this type. I want to abstract it, this type, what's the properties of this matrix that we know, and then prove it over. So what do we know about M? So I want to talk about KQT. This line. So I want to say that M is a KQT definition. M is a KQT design matrix if we have the properties that we see here. So the number of non-zeros per row is the smallest u, which in our case is 3. Okay, but I'll treat it as general parameter. Number of non-zeros per column is at least k, which in our case is delta n. So it's an M by N matrix. And the other thing we know, if you look at what happened here, when we pick these pairs, you ask yourself, if you have 2 columns in M, how many common non-zeros do they have? Well, every pair appears on a line and picks another point. So when we look at this point, it it will appear, its coefficient will appear in a point of this and the point of this. So at most 3, or depending how you count, most 6, the number of non-zeros in the intersection of 2 columns is that small. Let me call it T, which in our case is also 6, or you can put it 6, we just need the constant. Okay. So that's the design matrix.
Can you explain again the last part? Why is this?
Yeah, if you look at this and this, I want to say that there will be only few non-zeros. Why? So these are the 2 points you care about. So this point will appear, this point, we'll see the coefficient here occurs in this strip. Okay. And then we look at the lines for this point. So if we contain this line, so you will see a non-zero here again. But any point that any line that goes in other direction here will not, they'll not have a mutual non-zero coefficient. So anyway, it's simple. Okay, so we want to prove that every, so the theorem we are going to prove is that the rank. The main thing in this paper is that.
If you have like a ton of points on the same line, wouldn't they all appear in the intersection of 2 columns?
No, because I'm taking disjoint pairs. If you took all triples, you could have taken these ones and these ones, and yeah, but you don't. You make them disjoint. In principle, if there was one line, okay, just imagine one line, or maybe 2, I don't. One line, then you can make this matrix very long. You can make it have n cubed rows, but I'm letting it have only about n squared, right?
So
I'm taking this job.
Pairs.
Yeah.
You don't have pairs with respect to a specific point. You have pairs like globe. So
Yeah, arbitrary. If you pick them arbitrary. Yeah, you can. I mean, initially we picked them from a what's called 3 design. You can just have a collection of triples, so that no pair is in more than one triple, and then it's really easy to see, but I think that even this greedy method works. Anyway, it's very easy to arrange. Let's assume that it happens. So what we want to prove is that the rank of, in this case, if M is QKT design, then the rank of M is at least M minus N QT over K. Well, this is the first paper. So you see, if you case linear in N, you have just this constant 1 over delta squared. And what we did in this paper, we had several bounds in the paper with Shubangi and Zeev. Here we have, so one bound says that you really only need to square the cube. So it's really N minus NT Q squared over K, and you see how you get the delta instead of the delta squared. But if you want this rigidity result, there's another lower bound that you can prove that's very different, that doesn't have Q in it. It has N minus, here you have N squared T cubed over K to the fourth. And then if you are careful and apply it to some submatrix of the projective plane, you get linear low bound. But I'm just pointing this out, I'm not going to prove it. Anyway, but that's what we want to prove. Okay. Okay, so now you are faced with the usual problem of having a family of matrices that you want to prove for all of them a rank low bound. And first we'll do a sanity check. We'll just assume that all these non-zero coefficients are 1. Okay? So, toy case. M is 0. And just see. So here comes a little piece of algebra that is very simple. And okay, as we do in this third case, we look, in fact, in all the cases, we will look at A, which is M transpose M, right? Because we have this sparse condition. So let's look at what the property of so when we look at the diagonal of A, we see this case of the diagonal, right? And what do we see of the diagonal? Every pair intersects in a small sequence. So here we see a small sequence, right? And you should already, probably you've seen that, if you have high diagonal and low off diagonal, the rank is high. For example, if all the diagonals are 1 and all the off diagonals are less than 1 over n, or more generally, if in every row the diagonal term is bigger than the sum of the absolute values of the rest, then it's a full rank matrix. This is a triviality. So here we don't quite have the 1 over n ratio. We have general parameters, in fact. But still, there is a very simple linear algebra that was discovered many times. And I'll do it, let me do it here so I have room. But the place I fix it up is on the paper, nowhere along that I'll talk briefly about after I tell you the result. Anyway, it's a very simple calculation, so I'll do it completely so you see the power of Cauchy-Schwarz will give you an almost optimal rank low bound. That means something very close to n. Okay, so let's look at this matrix A. So first I want to say that I can assume as the diagonal terms are equal to K. Why can I assume this? This is a trick that will come big time soon, but it's a scaling trick. Suppose you multiply, if it's bigger than K, multiply the first row by some number less than 1 to make it exactly K. Do the same for each row. Then the diagonals are exactly K, and the off diagonal just became smaller. So that's okay. So we can assume it's exactly K. So let's look now at the trace of A squared. Okay, what's the trace of A? Kn. So this is Kn squared. But this is also the sum of the eigenvalues, right? So A is, as you know, this is a symmetric matrix, and so it's a Gram matrix. So it has real eigenvalues, lambda 1 up to lambda n. And so we can write lambda I. Well, and now we will do a Cauchy-Schwarz, right? So this is most n lambda I squared. And now this we know. This is basically the trace A squared, right?
And then
Times n. Okay, let me, before I write this second thing, I'll already tell you why I left the space here. If we do this, if we carry it out, we don't get anything. But the point is that D, we are assuming that the rank, we are assuming that the rank of A is n minus D, and we want to prove an upper bound on D. So for the Cauchy-Schwarz, we do it only for the non-zero term. So this for I equal 1 to n minus D. And so we can put this minus D here, and this will give us all the advances. Lambda I squared, so this is minus this is squared. Now we write the trace of A squared in terms of its entry. So this is exactly n minus D, a small c. We get here n K squared from the diagonal, plus at most n squared, which terms which are T squared. Right now, if you see what happens, this n is the main term here, right? N times n K squared. And what you get is, believe me, is so this is very simple. Okay, so what? I mean, we proved this for one special case, toy case of the whole family of. And now we start making observations. How do we generalize this further? You look at this argument, and you notice that we didn't use the fact that m was 0, 1. We actually used two properties. First, that if we call the columns of m, here, mi, m, these are the columns, right? So we use the fact that the inner product, namely the L2 norm of F, right? That's all we needed in this calculation. The other thing we need is that we look at mi and j, the I is different than j, and this is mostly. That's all we needed. Okay, so let's try to arrange it. So first of all, the upper bound here works for this type of matrices. But suppose the matrix we are given is not of this form. So now we look at M. and this down. And suppose we can arrange the following. That the L2 norm in every row, well, first in every column, is an, okay, so what do we want? Suppose the L2 norm is the same condition. And how do I call this? Let's call it J, the row, Mj, the L2 norm 1. Again, I'm forcing the L2 norm to be in the rows to be 1. L2 norm, the columns to be M over N. It makes sense that we have this ratio, right? Because we have maybe more rows than 4. If we can force it somehow, then we will be fine. So what are we allowed to do in order to force it? Here is a very simple operation. We can take, so I want this to happen. So if I'm given M prime that does not have this property, I want to multiply it on the left by some matrix and on the right by some matrix. Okay, for this also. So we want this M, and these guys are diagonal, positive. So this is called scaling. Again, if we can do that, a rank lower bound for M will be a rank lower bound for M prime. Why? Because scaling doesn't change the 0, non-zero pattern of a matrix, and it doesn't change the rank. That's all we want. So we are allowed to do scaling. So we should ask ourselves, when can we scale a matrix like that? And the answer is very simple, and it's in fact easier to do with L1 rather than L2. It doesn't really matter because the transformation between them is very simple. So, well, okay, maybe I'll do it in the proof. First, I'll set the condition. So M prime can be scaled. So scaled if and only if no zero rectangle, which is let's say a rectangle which is some rectangle here, combinatorial rectangle, okay, A by B, which is all zeros that you can find here. No zero rectangle satisfies A over M plus B over N is greater than 1. This is if and only. Okay, and I should correct this to say approximately, or this we can make equal. Approximately. Approximately, I mean that you can approach it, you can change your L prime and M prime so that you are very close. And then it's if and only if. And some of you should recognize this condition. Well, what does it remind you of? So I will remind you what it reminds you of, if you know, please. I did 2 reductions, one from L2 to L1, and then from rectangles to square matrices. Then you will see what it reminds you of. More efficient. And now she's getting interested. Okay. So first I want to say that this problem, this scaling in L2, is the same as scaling in L1. if you take any entry Mij and you send it to the absolute values, these are complex numbers. Mij squared, then of course conditional sums of squares become conditional. And this will give you a non-negative metric. And once you figure out L prime and R prime, you take square of the scaling coefficients, then you get the coefficient of the horizon. So that's no problem. So this is one reduction. What about the rectangle versus square? If you give me an n by n matrix, give me an n by n matrix, and you have this condition, row sum is 1 and column sum is m over n, you can simply take m copies here and n copies here, and be the big m by n mn matrix, and 0 blocks become 0 blocks multiplied by m here and by n here. And these are the maximal, because whenever you have here a 0, any 0, you can immediately duplicate it. So basically what you want is that here there is no rectangle, so that an plus bm is greater than mn, the size of the matrix. So you don't want a 0 block here. The sum of dimensions is bigger than the length of the side of the matrix. What does this remind you of? All condition. Okay. All condition. So basically we are down to okay. We have to scale. Now we will have m will be just a non-negative matrix. And we, in order to be scaled, in order for this model to be scaled, we want any a by b 0 block satisfies a plus b. Okay, then you can scale. Okay, so I'll tell you about how to scale and how this has to do with we want to be able to say that our matrix is scalable. In a second, just want to say this is a normal whole condition. So this is, we know that this is if and only if permanent and is positive, namely m has a perfect mean on the non-zeros. Right, that's whole theorem. Okay. I wanted to show you how, I want to prove the fact that you can scale over such matrix by giving you an algorithm to do it. I have time, but okay. I have time. But beforehand, let's see why our matrix, or almost our matrix, has this property. So our matrix, you can think of it, so maybe I should not call it. And I didn't write that. So why does our design matrix have the property we want? I claim that we have M is a QC design matrix. I can make it by twiddling it a little bit into a matrix that looks like this. Maybe by multiplying rows at most Q times. Okay, so I know that I can take my M, I know that I can put K, so the non-zeros here, right, and something. And then I take another K, which are non-zero in the second term. Maybe I copy a row from here, and so on. Okay, so if I want to understand the zero non-zero pattern here, or I know, in fact, all I have to do is to translate it to the square case and show you that the permanent is positive. This would imply the property I want. Here, so how many times I multiply it 3 times. If you repeat it k times, this structure, again, I have here 1, and so on, where if you have good eyes, you can see that you can permute the rows, the columns, sorry, that you see the rows, so that you see an identity matrix. Can I see it? If you don't see it, you can think about it. It's an identity matrix. So only these non-zeros guarantee the permanent is positive, and therefore that it has no hole blocker, and therefore that you can scale it, and we are done. So any matrix with this non-zero pattern, KQT design, can be scaled, and therefore the upper bound on the dimension or the low bound on the rank is right. Okay, so questions about this? We are essentially done. I want to show you how why this condition or why the permanence condition implies scaling. Okay, this is something I've shown many times in various forms of proofs, but I want to do it here because for those who haven't seen it and have learned a perfect matching algorithm in undergraduate, this is a very, very different algorithm for computing a perfect matching in a bipartite graph, and it's one that works totally differently, and it's not more efficient, but it certainly has the smallest program I know. It's in fact, it's probably the smallest program of any computational task I know. Okay, so let me go back to B. So what do we know about B? We are given a B, the permanent B is positive. In fact, maybe we want to test if the permanence of B is positive using scaling. So here's an algorithm. The algorithm basically tries scaling B. Tries to find the scaling of B because we said it's if and only if. It can be scaled if there's no zero hole blocker, if and only if there's a permanent is positive. So we try to scale B. Now, scaling B, what does it mean? Now we are in the square case. It's n by n, and we are trying to make it doubly stochastic, right? We won't. After multiplying it by, on the left and the right, by diagonal matrices. Now, it's a, non-trivial problem. It's non-linear. It seems like a fair problem because we have 2n degrees of freedom. These are the scaling coefficients for those in the column. We have 2n constraints. They are linearly dependent, but also here they are linearly dependent. So it's really the same number of constraints and degrees of freedom. So maybe you can do it. And of course, sometimes you can do it, sometimes you cannot. Like if the matrix is a zero matrix, you cannot do it. Okay. And okay, so what do you do? And this goes back. People like to quote Bighorn in 60-something, maybe 63. But it was discovered many times, this algorithm, and in various contexts, this scaling problem of a matrix occurred independently of everything we discussed, numerical stability of linear equations and signal processing. So it's a well-studied problem. And the following algorithm was suggested many times that it works. And let me write it also already in the form I wanted. You see it is efficient. So we'll do repeat n cubed times. So we want the row sums and column sums to be 1. But we can certainly make the row sums 1. We just divide every row by its row sum. Well, the column sums may not be 1. So we move and fix the column. So the sums are 1. Maybe we ruin the rows, we do it again, we do it again, we do it again. We do it n cubed times. Okay, let me assume that b was 0, 1, although for the general case there is also, you can modify the analysis. I'll show you the analysis only for 0, 1. So and then you test, let's say the last thing you scale was the columns, then you test if the row sums are close to 1. Up to 1 over n. Okay. So we know the columns are scaled and the rows are, either. And in the case of the yes, then you declare that the permanent of B is positive, and otherwise you declare that permanent of B is 0. Okay. So I want to show that this, in fact, sort of idiotic repetition of scaling columns has some virtue in it.
This is a polynomial time algorithm
This is a
for matching
Yeah, it's a polynomial time algorithm for matching you've never seen.
from 1937.
Yeah, I mean, essentially, nobody analyzed this like this. Basically, it was known implicitly in many papers that didn't care about matching.
And Edmonds didn't know it.
Edmonds probably didn't know it. Yeah.
Wow.
Edmonds cared more about, this Hungarian method is much older than Edmonds. Edmonds cared more about the non-bipartite case. It's just a bipartite case. I don't have an analog scaling.
Okay, Edmonds is for general.
Yeah. Edmonds not trivial results for general.
General.
No, I just finished with this analysis. So this analysis comes from a paper we wrote with, the proof, a paper we wrote with the linear, some more meat. And 2000, actually, this was a paper that influenced me and later work in many ways. This is just one of the examples. So those of you, again, from Yoming's talk, talking about operator scaling, so this also goes ideas from this analysis, and of course, various tools of invariant theory that here we will not make. So how do you analyze such an algorithm? You want to show that you make progress somehow. You are just alternating this rows and columns. You want to show that you make progress. And normally for any such dynamical system, this is a dynamical system. The algorithm generates a sequence of matrices, right? Or B. And you want to show that you make progress in this algorithms towards a scaling, or that the permanent is 0. It's very easy to see that if the permanent is 0, it will remain. Okay, so back up. To analyze something like this, you need some progress measure. And the progress measure we will pick, we see that it improved, will actually be the permanent of these matrices, B1, B2, and so on. And we'll show that it progresses. I just want to point out that if the permanent is 0, then it doesn't matter how you scale the matrix, it will remain 0. So what I want to show you is something interesting happens to the permanent as you progress. So we look at the permanent, and there are several things to notice. Okay, what we will prove, we'll prove 3 properties. Permanence of AI, when the I greater equals to 1 after the first scaling, is the smallest one. So progress measure usually want it bounded and then you see that you are getting closer to it, so you will increase it. All of them have permanent less than 1. Why is that? Well, every one of these matrices is scaled, at least in the rows or in the columns. The permanent is the sum of products of diagonals, but it's at most the product of the row sums.
AI is BI or?
Yeah, I keep saying. Permanent is any matrix B is a small and non-negative matrix system, the product of products of the RIs, so this also. Right? This includes the all non-negative. Okay, so this is trivial. The second thing that's obvious is this for 0, 1 matrix, after the first scaling, let's say, permanent of BI is at least 1 over n factorial. Well, in every, why do I say this? Yeah. We have at least, how many non-zeros do we have? Okay, that's not obvious. Okay, so need something. But we ignore this. It's simple. And any exponential of one will help because they will do the job because the permanent of BI plus 1, assuming that, let's say, it does rows, so assuming that some Ri minus 1 is bigger. So as long as there is a room to go when you scale, right, they are very far or somewhat far from being scaled already, will be bigger by 1 plus 1 over n and the permanent BI. And if you have these 3 properties, you see that you convert in polynomial time. Right? So I just have to show you this, and very good. And I'll just show you that it grows, and you see from the proof, you see that you can get this factor if you have this condition. But without any other condition, the permanent increases. So why is this? And I apologize for the people who've seen it. So what is the permanent of BI plus 1? The permanent of BI. Let's say we have the row scaled and we are scaling the columns, or we are scaling the rows, doesn't matter. So when we are scaling, let's say the rows, this is product 1 over R1, right? This, to make the row come to 1, we divide every row by its rows, right? So we change, so this will be the scaling right now. So the permanent, of course, will be affected in the same way if you scale the row. It will go down by 1 over, by the product of 1 over R. Everybody's happy with it? And now we use the arithmetic geometric mean. And we know that the product here is the most I and right. But what is the sum of Ri's? We don't know the Ri's, but the sum of the Ri's is the sum of the CI, of the columns. What's the sum of the columns? They're all 1, so their sum is n. So this is 1. So AMGM guarantees that this increases, and if you remember, AMGM is typed precisely when all of the terms are equal. And AMGM itself tells you that if you are far from them being equal, you get a gain which you can easily calculate, and you get this. extra function. So I think this is all I want to say.
May I ask for the scaling part? So when we come back to the delta Sylvester-Gallai, so basically improve the quadratic to linear, right? That's there.
It's a calculation. It's not you are losing something in that original argument with the ranks.
We are scaling here to restore.
Yeah, no, it's not related to the, even before the scaling, it's in this, this algebra. Yeah, you need to be more careful.
Any more questions? Is there is this the only proof you know for this theorem?
Yeah, it's the only proof I know.
There's no polynomial method.
No, I don't know anything that doesn't use scaling. Yeah. So I should mention somebody, Max mentioned the Foster results about sign rank, or I mentioned it also. Also there, it's a property, it's of any with the same signs. You assume the rank is low, so you write it as a product of narrow matrix and basically a set of vectors, and you don't know anything about them. Then you scale them. You scale them in a different way than I'm scaling. It's not a scalar scaling. I mean, you do scalar scaling to put them all on a sphere, but then you do another scaling, which is a linear transformation, to put them in some kind of uniform isotropic position. And the existence of this scaling is one of the things that started this whole operator scaling business. But scaling is used also there. But there are other results about patterns in, having a result about everything that fits a pattern, and which doesn't use scaling.
But can you recover the old Kelly proof from this somehow, or?
The Kelly
exact...
is a bound gives you Kelly proof. Yeah,
but I mean, these are very different proofs.
You recover it. You prove that this is the rank is at this n-1, n-2. Yeah, you are extremely careful with it. Shubhani is extremely careful with the constants. And you can get the rank to be n-2 and delta is 1.
It's recovering the result, not the proof.
No, it's a proof. What do you mean? This is a proof. You prove an upper bound of 2 on the dimension of any complex ST configuration. Of course, it's a proof.
It's a generalization of the proof itself.
Yeah, I was just curious how it relates to this proof, but we can take it to
Okay. More questions. Okay, thank you.